Alrighty, the two chapters on the test, 19 and 20. 19 deals precisely with the idea of electric current, which you see right here, and things that affect electric current like resistance, and then also how current plays into power. Go through your section objectives. Make sure that you can answer these basic things. You do know what's going on in the chapter. And in this very, very first piece, of course, they highlight the idea that the movement of electric charges is actually how we define current. So make sure that when you're talking about the idea of current, you know that we're dealing with moving electric charges, not electric charges which are stationary. That's static electricity. However, go back a second here. Be very, very, very sure you realize that current is the rate of charge motion, not just how much charge moves, i.e., how much charge has passed, but also how much charge has passed per unit time. So make sure that you can work with this formula, that current is charge divided by time. You know how changing each of the variables would affect the amount of current, more charge, more current, more time, less current, etc. And be able to actually work some problems. Know that the unit, of course, is the ampere, and that the ampere references 1 coulomb per second. So 1 amp is actually a lot of charge moving per second. We had some sample problems, practice that you worked in this particular section, 19A. Yes, there are going to be 1 or 2 problems like this on the test, so be prepared to work on them. Know the difference between conventional current and just the generalized direction of charge motion. Conventional current is always defined in terms of positive charges, whether the actual charge carriers in the wire or the solution or the object are positive, negative, or a combination of the two. So you see a nice little table down here, table 19.1. Conventional current is always going to be referenced as if it's positive. So this right here would look at, whoa, that's a little bit much. That guy and this guy are both showing the idea really of what conventional current would do. If I'm monitoring positive charges, yes, that's the direction of, conventional current. But in the case of an electron, which we know most commonly is going to flow through your wires, it will be opposite the direction of conventional current. Now, as we talk about the motion of charges through something like a wire, the concept of drift velocity came up. A lot of people think that when you are dealing with charges in something like a wire, they move at an extremely, extremely, extremely rapid rate. That's not true. What does move at an extremely rapid rate is actually our electric field. Our electric field does move at nearly the speed of light. So when you turn your light switch on, the lights come on immediately. The charges themselves, however, are creepers. The term drift velocity references the net velocity of the charge carriers, meaning every single one of these little arrows over here in 19-2, which are velocity vectors, could be very, 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 very high. Problem is, you got a lot of positives added to a lot of negatives. The sum, or the net value, is actually not terribly great. So charges moving through wires have many collisions with the particles in the wires. And we talked about how the collisions generated increased kinetic energy for those atoms. It also generated friction from heat, and this is why electronic systems heat up so easily. And every collision provides a new velocity vector. The overall drift velocity then, how much distance does our little, I don't want all that highlighted, how much distance does my little charge make in reference to a certain amount of time? And those velocities are actually very small. They give you a value here, 2.46 times 10 to the minus 4 meter per second. That's not at all aberrant in any way, shape, or form. Let's see. Sources and types of current. Sources of current, batteries and generators. These guys provide the potential difference, the high electric potential and low electric potential ends of a circuit that stimulate charge motion through the circuit. They also, though, supply energy to the charge carriers. So they're also the ones who are pushing them back up the potential gradient, filling them up with energy. For battery, that energy for that push comes from chemical energy. When we're looking at the idea of a generator, it's coming from mechanical energy. So there's always a source of energy to transform to another source. And then ultimately, those energies will become electrical energy. Current can be direct or alternating. Know who gives me direct current? Battery. Who gives me alternating current? Generator. Know that direct refers to a single direction of charge motion because there's a single high and a single low electric potential associated with the battery. We have a positive terminal. We have a negative terminal. And guess what? They never change. So there's always one direction of charge flow. In AC, though, the terminals of the source are constantly changing sign. In other words, they're going negative, positive, negative, positive, negative, positive, back and forth, back and forth, back and forth, back and forth. For US, at a frequency of 60 hertz or 60 times per second. So the charges are always in motion, but they go one way and then the other, one way and then the other, one way and then the other, alternating their directions back and forth. You should know, what does resistance mean? The opposition to the motion of charges within something. And how Ohm defined it mathematically. Ohm defined that the property of resistance, give my charges a certain amount of potential difference, i.e. give them so much energy per charge, at how fast could they run? What was the rate of the current, or what was the current? Now, for things that follow Ohm's law, and of course the unit for resistance is the ohm, for things that follow Ohm's law absolutely to the letter across a very wide range of potential differences, we call those substances ohmic substances. So things that are ohmic always are going to follow Ohm's law. And if I actually graphed out an ohmic substance with current and potential difference, I get a nice straight line. However, there are a lot of things out there that are non-ohmic, including light bulb filaments and diodes. Graphing current versus potential difference, I would see a different resistance at different points. So you should know the difference between ohmic and non-ohmic. What type of graphs would they make? You should know what Ohm said about resistance. And they throw in here the little idea of diode. A lot of you worked with diodes in lab. Those guys are non-ohmic. They're actually there to control direction of current. So in one direction, they don't flow at all. You don't see charges moving through them. It's only through a different direction that we will see charge motion. So we consider those guys non-ohmic. This particular table I have emphasized you need to know, and I'm going to emphasize it again. Factors that affect resistance, the big four: length, cross-sectional area, material, and temperature. You should know that list, and specifically what do they do. So a question could read something like, list and describe factors that affect the resistance of something. I would expect to see length, shorter length, less resistance, greater resistance for longer lengths. Cross-sectional area, thicker wires, less resistance, thinner wires, more, etc., etc., etc. Or be able to compare. If I gave you some different conditions, who would have the greatest resistance, who would have the least. You should know the job of a resistor. Control the amount of current in a conductor. There's one battery, that's all there is, we're assuming, has one potential difference, and therefore if I need different amounts of current, what I can do is add different types of resistors into the mix. So it's usually a quicker, cheaper, and easier way to influence the amount of current in a circuit. Changing the potential difference source is very difficult. So be able to work problems here with Ohm's law. Okay? Just nice, straightforward Ohm's law problems, but make sure you can work them. And of course, we know that we need them heavily in Chapter 20. I said don't worry about the idea of salt water and perspiration, not an issue, or the idea of variable resistors. We're not going to worry about that for our purposes. However, we are worrying about superconductors. Know that superconductors, when they get to a certain critical temperature, which is pretty cold, we don't have any room temperature ones yet, the resistance goes to zero. It doesn't go low, it goes to zero. Because of that, with a resistance of zero, if I attached a superconductive material up to a battery, got some current flowing, I could take the battery away completely, and the current would continue to flow. For years and years, potentially, we've seen in lab. Things that are really, really good conductors, like copper, silver, and gold, are not superconductors. And things that are kind of crummy conductors, like aluminum, tin, lead, zinc, are superconductors. So there's no relationship between your conductivity properties at room temperature and whether or not you're going to be a superconductor. Beyond flat out just maybe the definition of Meissner effect, which is if I have a superconductor, we can see levitation with the permanent magnet, don't worry about Meissner effect. We did talk about it in class, but it's not going to show up on the test. Electric power will, though, so make sure you're very, very clear about what electric power is, that it is, yes, a rate function. So again, we have a rate of energy delivery, rate of energy transfer, rate of energy conversion, rate of energy use, rate of energy dissipation, rate of work being done. However it comes to be defined, make sure you're honing in on the fact that it is a rate function. It's always something per time. We had 3 formulas to calculate electric power. 1, the product of current and voltage. And if we throw Ohm's law into the mix, we actually get a couple of other formulas. I square R and V squared divided by R that can all be used to calculate power. These 2 formulas at the bottom here actually though illustrate the difference between sending energy per time at high current versus the equivalent power, energy per time at high voltage. If you have high current with the same resistances, you're going to wind up getting a lot more friction. So unfortunately, a great deal of that power is going to be simply dissipated as heat energy and not maybe useful work. Now that idea is called Joule heating, or I square R loss. For something like a space heater, toaster, hair dryer, things like that, it's great because we want heat from them. But for other devices, we want more energy delivered as useful energy, and therefore sending it at a higher voltage avoids the I square R loss problem. We worked some basic power problems. You should be able to do those. So those guys back here. Don't worry about electric companies and their kilowatt hours or cost of electric energy, but do remember why electric energy is transferred at high potential differences and not high currents. So for the same amount of power being delivered by a power plant, we send it at high voltage to minimize that I square R loss. And we talked about how we use step-down transformers and things like that to finally get the power to what is appropriate for a household setting. Now, if you never do, it's always a good idea to go back to these key ideas at the end of every section. It's not comprehensive, it won't have everything, but at least it'll give you some highlights, things to look at. I mean, your study guides are online, but here's an additional thing you can look at. Formulas, sometimes all of them are there, sometimes they miss a couple. So don't just go here and say, this is all I have to know. Don't forget your note packs, don't forget this, and obviously formula sheets will be available for you on the test.